Let's have a look at how much water is in the container. At time t. We know it starts off with 3. We know contaminated water is coming in at a rate of 1/4 litre per minute, so that's a 1/4 t. And we know it's leaving at a rate of 1/8 of a litre per minute, so that's minus 1/8 t. If we look at the contaminant entering, okay, we're told this is 5 minus e to the minus 0.1 t milligrams per litre, and there's 1/4 of a litre entering every minute, so this is over 4 is the amount of per minute. It's just 1/4 of a litre, that's per litre, so it's 1/4 of a litre. So let's have a look at the rate it is entering. So the rate of contaminant entering, if you like, is that. And the rate of the contaminant leaving well, we know, what do we know? Here we've got the water in the container is 3 plus 1/8 t, and we know there's m, so it's m over 3 plus 1/8 t. So this is the concentration of a contaminant. So m is the amount of contaminant. That is the volume of water in the container taken from the top. And we know the amount that's leaving is 1/8 of a litre. So we times it by 1/8. Okay, so that comes out to be m over 24 plus t. So that gives us the result we're looking for. So dm by dt over 4 okay, so if I move the m across to get into the standard format, plus 1 over t over 4. So the integrating factor is e to the integral 1 over 24 plus t dt, which is e to the log 24 plus t, which equals 24 plus t. So that implies the differential of 24 plus t m equals 24 plus t times 5 minus okay, that's a default. It's a differential of I times m. I'll perhaps be more obvious if I multiplied throughout by 24 plus t, but okay, so I've got that. Which I can expand the right hand side. So I get 120 plus 5t, take away t, e to the minus 0.1t, take away 24 e to the minus 0.1t. I'll move the 4 across for a minute. Okay, so integrate both sides. I get 4 times 24 plus t lots of m equals the integral of this side. Some bits I can integrate easily, so it's 120t plus 5 over 2t squared. And this is e to the minus 0.1t, so there'll be a 240. 24 divided by minus 0.1, and then I've got the other bit, which is a tricky bit, plus the integral, is it plus? Minus the integral of t e to the minus 0.1t dt. Okay, so it's this bit I'm interested in. Okay, so move that up. So I'll do it in blue. The integral of t e to the minus 0.1t dt. Got to do by parts. So I've got, this is u, this is v dash. So u dash equals 1 and v equals minus 10 e to the minus 0.1t. Plug them in using integration by parts. U times v, so it's minus 10t e to the minus 0.1t plus, take away the integral of u dash v, so take away minus, okay, so plus integral of 10 okay, which is now easy enough. Take away 100. Don't forget, you must include that c before we do any manipulation at the end. So now, going back to my black pen, I've got 96 plus 4t lots of m, 120t, 5t squared over 2 plus 240. Ooh, I've got 240. Take away this, so plus 10t plus 100 e to the minus 0.1t plus c. Okay. So what I've got to do, so I know that t equals 0, there's no contaminants. I'll plug that in, 0 here, 0, 0, 340 times 1 plus c. (340) plus c equals 0. So c is minus 340. So therefore I'm left with m equals 120t, 2.5t squared, 340 e to the minus 0.1t, 10t e to the minus 0.1t, take away 340, all divided by the 96 plus 4t. Okay, and then it says after 30 minutes the concentration was measured as that. How does the model stack up? So t equals 30. We plug that in, we get m equals 25.657, and we get the volume equals 6.75. Okay, so the model predicts a concentration of 3.80 milligrams per litre. That divided by that, which I would say is very close to the measured amount. And could be explained by measuring inaccuracies. Whichever way you put it, the model seems to be very close to what is actually measured.